Hi, and welcome to the fourth session of the ArcQuest Basic Stats and Interpretation course. My name's Lauren, and I'm going to talk you through this session on risk and odds. Our learning objectives for this session are to understand and interpret, firstly, risk differences and risk ratios, followed by odds and odds ratios. And all of these measures are used when we're interested in binary outcomes. So first we have risk, and risk is a basic concept that most of us use or hear about quite often. So think about the risk of being in a car accident or the chance of winning the lottery. We tend to use the words risk and chance and probability all quite interchangeably, depending on whether the outcome is something that we think of as positive or negative. And the definition of risk is the number of new cases with an outcome of interest divided by the number of cases initially without that outcome. So for example, if you took a group of 10 women aged over 60 without breast cancer and followed them up for a year, and one of them developed breast cancer during that time, we would have one new case and 10 cases in our sample who didn't have breast cancer at the beginning of the year. So this is 1 out of 10 women developing breast cancer, which equates to a risk of 1 divided by 10, which is 0.1. And we could also refer to this as a risk of 1 in 10 or 10%. And in research and evaluation, we're often interested in comparing the risk in two groups. And to do this, we can use risk ratios. And the risk ratio is the risk in one group, so for example, some exposure or intervention group, divided by the risk in another group, so for example, an unexposed or a comparison group. When comparing risk in two groups, it's often helpful to develop a 2x2 table such as this. So we have our 2 exposure groups or comparison groups of interest on the left-hand side and our 2 outcome groups at the top. And we can fill in the table with the numbers who fall into each category. So in box A, we would put the number of people who are exposed, so this could be smokers, for example, and who also experience some outcome of interest, which could be lung cancer, for example. We would then complete the rest of the table by adding in the numbers of people in each of the other 3 categories. Then, based on the numbers in the tables, we can calculate the risk of experiencing the outcome in each of our exposure groups. So for the exposed group, this would be A divided by A plus B, and for the unexposed group, this would be C divided by C plus D. Here we have a hypothetical example considering the association between smoking and lung cancer, which will hopefully make it all a little bit clearer. So here we have smokers as our exposed group, and non-smokers as our unexposed group, and lung cancer as our outcome of interest. So to calculate the risk of lung cancer in the group of smokers, we would calculate 130 divided by 1,000, which gives us a risk of 0.13 or 13%. And to calculate the risk of lung cancer in non-smokers, we have 50 divided by 4,000, which gives us a risk of 0.0125 or just over 1%. So we can see from this that the risk is much higher in smokers than non-smokers, which we would expect. And then we can quantify how much higher the risk of lung cancer is in smokers than non-smokers by calculating a risk ratio, which we can do by dividing the risk in the smokers group divided by the risk in the non-smokers. And if we do this here for this example, we would calculate 0.13 divided by 0.0125, which gives us a risk ratio of 10.4. And this tells us that the risk of lung cancer is 10.4 times higher in smokers than non-smokers. This risk ratio interpretation is important. So if you have a risk ratio of 1, this tells us that the risk is the same in the 2 groups. So whatever your risks are, if they're the same, when you divide one by the other, you're going to get 1. So this tells us that there's no association between the exposure and the outcome. A risk ratio of greater than 1 tells us that the outcome is more likely in the exposed group than the unexposed group. So for example, if we had a risk ratio of 1.7, this tells us the outcome is 1.7 times more likely in the exposed group than the unexposed group. Or another way to describe this is that it's 70% higher in the exposed group than the unexposed group. Similarly, a risk ratio of less than 1 tells us the outcome is less likely in the exposed group than the unexposed group. So for example, if we had a risk ratio of 0.58, this tells us that the outcome is 0.58 times as likely in the exposed group as the unexposed group. Or another way to describe this is to say that the risk is 42% lower in the exposed than the unexposed group. So as you can see, there are a few different ways that you can describe a risk ratio. And this is generally down to personal preference, but as a rule of thumb, I'd usually say that if a risk ratio is greater than 2, I'd usually describe it using the number of times greater. So a risk ratio of 2.5 would say that the risk is 2.5 times greater in the exposed than the unexposed group. If a risk ratio is between 1 and 2, I'd usually describe it as the percentage increase. So like in the example we have here, a risk ratio of 1.7 would be described as an increase of 70% in the exposed compared to the unexposed group. And if the risk ratio is less than 1, you can either describe it using the two examples on the slides. So a risk ratio of 0.58 tells us that the outcome is 0.58 times as likely in the exposure group, or that it's 42% less likely in the exposure group. Or you could say something like, the outcome is almost half as likely in the exposure group. And as with all the comparisons you've heard across these sessions, it's important to present confidence intervals and p-values alongside a risk ratio to help with interpretation. So for our example on smoking and lung cancer, we had a risk ratio of 10.4, and this has a 95% confidence interval of 7.45 to 14.52. So what this tells us is that we're 95% sure that the true risk of lung cancer is between 7.45 and 14.52 times higher in the smokers than non-smokers. And we also have a very small p-value here, so we're confident that this is a true difference between the two groups. And always remember that association does not equal causation. So just because two things are associated, it does not necessarily mean that one causes the other. So far we've considered risk ratios to compare two risks, but another way that we can compare two risks is to take the difference in risks, and to do this we can take one minus the other. And this gives us a different measure, which is sometimes more useful in understanding the impact of the exposure on a population. So a risk difference has units, and this is usually presented in terms of the risk per 1,000 or risk per 100,000 people. Using the same example of smoking and lung cancer from before, we can calculate this risk difference. So we have 0.13 minus 0.0125, which gives us 0.1175. And what this tells us is that the increase in risk of lung cancer in smokers is 0.1175 per person, or more intuitively, 11.75 per 100 people. So this tells us that for every 100 smokers, there will be on average an extra 12 lung cancer cases compared to a group of 100 non-smokers. And this makes sense because we had a risk of about 13% in smokers, which is 13 in 100, and approximately 1% in non-smokers, which is 1 in 100. So you can see that that's a difference of approximately 12 per 100 people. So in summary, a risk ratio tells us how many more times the outcome is likely to happen in one group compared to another, and it's a relative measure looking at the strength of an association. And in contrast, the risk difference has units, and it tells us about the impact of the exposure by comparing absolute differences. And you'll find that the risk ratio is more likely to be used in research or evaluation, but that risk differences might be more often seen when you're communicating findings with patients or the public. So if we relate this back to the e-cigarettes example paper that you were introduced to in the introduction session, the authors have presented the number and the percentage of patients in each of the exposure groups, and then also presented the relative risk, which is just another word for risk ratio, and also the risk difference. So if we take the 1 month data, for example, you can see that this data was calculated from a 2x2 table. So to understand where the numbers that they've presented come from, we can recreate this 2x2 table. And what you can see is that there were 67 people in the nicotine e-cigarette group who successfully stayed abstinent from smoking, and that was out of 289 people who were in this group. So our risk of abstinence in that group is 67 divided by 289, and similarly the risk of abstinence in the placebo group was 12 divided by 73. And you can see that they've presented those numbers in the table. And then the risk ratio is simply the 0.2318 divided by the 0.1644, which gives us a risk ratio, or relative risk as they've called it, of 1.41. And then the risk difference is one minus the other, which gives us 0.0674, which is equivalent to 6.74 per 100 people, which is what they've presented here. Okay, so now we come on to odds. And odds is a similar concept to risk, but it is subtly different. So a quick reminder about risk. This is essentially the probability that an event will occur, or technically, the number of new cases with an outcome divided by the number who initially did not have that outcome. And odds are similar, but note the difference in the denominator. So here we have the number of who had the outcome divided by the number who did not have that outcome. So if we had 10 people and we followed them up for a year and one person had a heart attack, then we would say the risk of a heart attack is 1 in 10, or 0.1. And for odds, we would instead divide the one case with the outcome by the 9 cases who didn't have the outcome, giving us an odds of 0.11. And note that in this example, the risk of 0.1 and the odds of 0.11 are quite similar, but this is not always the case, and I'll demonstrate that now. Here in this example, we have a rare cancer. So you would calculate the risk as the number with that cancer, coloured blue here, divided by the number of people in your sample, so all those that are coloured both orange or blue. And to calculate the odds, you divide the number of people with cancer again, this is the blue group, by all the people who didn't have cancer, so this is the orange group. And you can see that because the outcome is rare, this denominator is very similar for the odds and for the risk, and therefore we'll find very similar results. Alternatively, if we have a cancer that is less rare, so our outcome of interest is not rare, the denominator for the calculations of these two are quite different. You can see that the denominator to calculate the odds is much smaller than that for the risk, and therefore the odds will be a much larger number than the risk. So for rare outcomes, usually outcomes that occur in less than about 10% of your sample or less, odds approximate risk. But for more common outcomes, this is not the case. So this is something you need to bear in mind when you're working with odds. So just like how we can use risks to calculate risk ratios, we can also use odds to calculate odds ratios. So an odds ratio is calculated by the odds of an outcome in the exposed group divided by the odds of the outcome in the unexposed group. And from our 2 by 2 table we saw earlier, this is A over B divided by C over D. So just a quick reminder of how our 2 by 2 table is laid out. To calculate the odds, we just need the 4 numbers in the centre of the table, our A, B, C and D. And we don't need to worry about the totals. Here is another hypothetical example. So here we have an exposure of severe sunburn in childhood and an outcome of malignant melanoma. And in this example we have more people in the unexposed group, those that are not exposed to severe sunburn, than in our exposed group who were exposed to severe sunburn. So using this data we can calculate the risk ratio and also the odds ratio. So remember, for the risk we calculate the number in each group with the outcome divided by all people in that group, whereas for the odds we calculate the number in each group with the outcome divided by the number of people who did not have the outcome. And if we do that with these numbers here, we find that the risk ratio of 4.0 is very similar to the odds ratio of 4.02. And this is because the outcome here is rare in less than 1% of people, and therefore the denominators for the odds and the risk are very similar, so we end up with very similar risk and odds ratios. Now you might be thinking, why would odds and odds ratios ever be used? They seem less intuitive and often provide very similar answers. Well, one of the reasons that we need to use them is if the data comes from a case control study, we do not know the true totals for each group, because we've identified people on the basis of whether or not they had the outcome. So in a case control study, it's not possible to calculate the risk ratios, but we can still calculate the odds ratios because we only need those 4 numbers in the middle of the table and not the totals. So we can do this instead. And the other reason we may use odds ratios is if we want to adjust an analysis for confounders. So for this, we'd need to use logistic regression, which produces odds ratios rather than risk ratios. And I will briefly touch on logistic regression in a minute. And just to reiterate, as I've mentioned before, for rare outcomes, the odds ratio will be a good approximation of the risk ratio. So given a rare outcome, we can interpret the odds ratios as risk ratios. So if we have an odds ratio of less than 1, this tells us that the exposure is negatively related to the outcome. And if we have an odds ratio of greater than 1, then this tells us that the exposure is positively related to the outcome. But if the outcome is not rare, be aware that the odds ratio will overestimate the strength of the association between the exposure and the outcome. So if we have a risk ratio of greater than 1, then the odds ratio will be greater than the risk ratio. And if you have a risk ratio of less than 1, then the odds ratio will be smaller than the risk ratio. And finally, I want to touch on logistic regression, which I mentioned a minute ago. I'm not going to go into any detail about how to do this, but I just want you to be aware of it and when it might be useful. So the simple odds ratio, calculated from the 2 by 2 table, does not take into account any confounding variables. And a confounding variable, or a confounder, is a variable which is associated with both the exposure and the outcome. And this can therefore mess up the association that we see between the exposure and the outcome if we don't account for this. And age and sex are very common confounders that should be considered in almost any non-randomised study. So focusing on our example of sunburn and melanoma that we had a minute ago, a potential confounder for this is age, and this is because older people might be more likely to have been exposed to severe sunburn, as people were less worried about sun cream years ago, and also older people are more likely to develop melanomas than younger people. So in this example we had an unadjusted odds ratio of 4.02, for which we could calculate a 95% confidence interval and p-value, which we've presented here on the slide. And if we want to adjust for age, we can use logistic regression. And as I said, I'm not going to go into how you do this, but if you did adjust for this, then we would find an adjusted odds ratio of 3.79 with the associated confidence interval and p-values presented here. And this is not too different for the unadjusted odds ratio in this example, but the adjusted odds ratio is a little smaller and the confidence intervals are a little wider as age has been introduced and therefore introduces more uncertainty into our estimate. And it's common for the size of the odds ratio to be reduced or get closer to the null value of 1 when we control for confounders. And it's likely that if we controlled for other confounders, perhaps sex or socioeconomic status, for example, then we might find that this odds ratio reduced even further. So in summary, risk and odds can be calculated to describe binary outcomes, and risk ratios and odds ratios can be used to investigate the relationship between 2 binary variables. And risk usually feels easier to interpret, but the use of odds may be required instead in the case of a case control study, or if you want to adjust analyses for confounders using logistic regression. And finally, when the outcome is rare, approximately 10% or less of your sample, then odds and odds ratios will approximate risk and risk ratios. And that's it for this session. Thank you for listening.